Thank you, Costa, and thank you very much for the invitation to be here. For at least a couple of decades, most of my career was with government in soil carbon research. I've worked for big companies in the Nature-Based Solutions program, and with Impact Ag Australia, I'm their chief scientist. So we've got farms across Australia where we implement regenerative ag practices, but really importantly, evidence-based practices. So I'll be kind of talking a little bit about what we do, but mostly about what you guys can do on your farms. Now, when I was given this topic around strong soils, secure futures, there was a big list of things for us to cover. So what I decided to do is I've put together some quite comprehensive slides, which I've said can be available after the talk, so you're free to have those, and I'll just touch on some of the slides as we move through them. So there'll be more detail in the slides, but really encourage you to kind of listen along as we go on this journey to talk about the importance of soil health and what you can do on your farms to drive that system to support healthy crops and pastures and trees and grow nutrient-dense food. So I want to start with the concept of soil organic matter. So when we're thinking about the decades worth of research that we've got here in Australia, it's all underpinned healthy soils by increasing soil organic matter. And the reason that is by increasing soil organic matter, we drive the biological system in the soil to glue particles together, to make nutrients available to our plants, to make sure that we've got adequate moisture and air in the soil as well. So that's essentially what we're talking about. So if we look at this graph here, this is for a chroma soil. Don't need to know, chroma just means that it's bright in colour in the subsoil. It's a duplex soil, so it's a sandy soil over a clay soil. But the main thing I want you to have a look at this graph here is on the x-axis, which is the landscape one that's going along the bottom. It's the relative effect of soil organic matter on productivity and sustainability metrics. On the y-axis, so you can probably see it better if you look to the side screens, if you're sitting on the side, it has a range of processes that we like to influence and that help us have productive, profitable farming systems. So things like biology and biodiversity, cation exchange capacity, so the soil's ability to hold on to and exchange nutrients, nutrient storage and cycling, the tilth and friability of the soil, water holding capacity, aeration. So the longer the bars that you see on this graph here, for this particular soil type, the more important soil organic matter is. If we look at a different soil type, for example, organic matter is just as important. This is a black vertisol, so a soil that cracks and heavy in clay. It's a gradational soil profile, which means it gradually gets heavier in texture as you move down the soil profile. And you can see soil organic matter is still important, but its role in providing some of those functions is less, and that's because we've got a clay-rich soil. So context is everything. But it's soil organic matter that drives soil health. Now, the way that we measure soil organic matter is by measuring the carbon content of the soil. So soil organic matter is 58% carbon by weight and it's 42% other stuff. And it's the other stuff that feeds our microbes in our plants. So things like nitrogen, phosphorus, potassium. But carbon is the measurable component, and that's why that's what we look at on our soil test results. So if we think about how do we build carbon in the landscape, and we've got a range of different experiences and knowledge in this space, but I want to start, excuse the pun, from the ground up and take you on a journey about building carbon in our landscapes. So all of this is embedded in our literature, and in New South Wales in particular, we've got a huge amount of peer-reviewed scientific literature about the practices which can increase soil carbon. So the way carbon gets into our soils is primarily, other than if we're making compost and bringing compost to the site or another organic amendment, is through the process of photosynthesis. So as plants grow, they photosynthesize. They take carbon dioxide from the atmosphere, they use energy from the sunlight, and they take that carbon from being in a gaseous form in the atmosphere into a liquid form in the plant itself and a solid form. So we have carbon accumulating above ground in leaves and stems, in manure when we have grazing livestock grazing on that, below ground roots and root exudates. So root exudates are those carbohydrate-rich signals that the plants leak out into the soil to attract microorganisms to live within the rhizosphere. So the rhizosphere is that thin film of soil around the roots. So when you dig up a nice healthy plant, kind of hard in a clay soil to see it, but in a sandier, lighter soil, you'll see root dreadlocks. Essentially, that's the rhizosphere. Now, the important thing about root exudates is the plant biologically, evolutionary over millions of years has developed the capacity to change the signal of those root exudates depending on what it needs. Because if you're a plant, your whole digestive system is on the outside, right? So we eat food, we've got microbes in our gut and we can get nutrients out of it that way. For a plant, their digestive system, the microbes are in the soil. So what they do is they leak out carbohydrates and signals to encourage microorganisms to live within their rhizosphere around their roots so that they can access nutrients. So it's really important, like a carbon economy that happens. So nearly every nutrient to become plant available, which usually we say it's in the 8 format, like sulfate, nitrate, phosphate, needs to first pass through a microorganism for the plant to be able to uptake it. So it's really important. So the plant exists to feed this microbial community. So more than 60% of the total photosynthesis capturing carbon dioxide goes below ground, and nearly half of that will leave the plant roots in terms of root exudates to support that really important process. Now, once organic matter is in the soil, we start to refer to it as soil organic matter. So for a dirt nerd like me, that means that it's got to be less than 2 millimetres in diameter, and we've got a way of classifying that. But when we're thinking about the role of organic matter in soil, it doesn't matter how bloody big it is, right? If it's a nice big long root or fungal hyphae wrapped around aggregates, that is performing the function that we need it to perform. When we're looking at soil test results, we're looking at it on standardised fraction, which is a dried soil at 40 degrees, it's been crushed up, and it's the less than 2 millimetre fraction. So, less than 2 millimetre fraction because that is the fraction of carbon that is correlated with those stack of benefits that I listed on the first graph. So that's why we have that there, standardised across labs. Once organic matter is in the soil, it can be protected. So when we're talking about being protected for longer term storage, it's protected from the microorganisms, right? So it can be wrapped up nice and tight in a soil aggregate, a crumb of soil. It might be stored nice and deep down in the soil profile where there's less biological activity compared to our surface soil. And so it's a physical protection. So if we're just thinking about this flow of carbon so far, if you've got practices which are growing bigger, healthier plants, so they've got adequate nutrition, you're grazing well, in orchards, for example, you've got cover crops and you're managing your interrows well, you're capturing more carbon dioxide, so more solar panels on your farms, in your orchards, then you are maximising that carbon flow into the soil, overcoming soil constraints. So that's a really important factor. The other next really important thing is around ground cover. So cover is king or queen in this case. So really important practices which are managing ground cover. So we know that we can build soil structure through practices which keep ground cover and keep a lot of carbohydrates flowing into the soil. Now, organic carbon can also be protected in different ways. So clays in our soil also have the ability to hold on to organic carbon molecules. So they can store it. Just like a bank, they can store more. So the more clay you have, the more carbon your soil just will inherently be able to accumulate. Microbes are also a really important store of stable carbon. So when we think about if you've got a nice handful of rich compost, it gets dark in colour because of the humic staining, the humus. So what humus is it's microbes and microbial detritus. So the more microbial activity you have, the more humus that you have, the more stable that carbon becomes in the soil as well. So we've got different stability of carbon in the soil. We can get a bit fancy and measure this, so we can look at the total organic carbon pool. So if you send a sample off, I saw Graham here before, to EAL, and you use the combustion test, dry combustion test, that tells you total organic carbon, or you can look at the fractions, the type of carbon, and really that looks at how quick that carbon's going to turn over. So the labile carbon, or the particulate organic carbon here in this graph, that's typically your carbon economy, feeding the microbes and driving some of those systems. Your humus, or your mineral-associated organic matter, is what we call it these days, but it's basically humus. I've got a really good sense of humus. And it's kind of your more stable nutrient store of carbon. And then you've got charcoal. So in our Australian soils, through a long pattern, we're talking tens of thousands of years of burning across our landscape, we have a huge amount of really fine charcoal in our soil. And that in Australian soils can be as high as 35% of that total organic carbon, right? So some of this we can influence. So can't influence charcoal easily. Mineral-associated organic carbon by practices which promote microbial activity, we can influence that. And certainly labile carbon, fresh organic matter going back into the soils is something that we can influence with our management. But this is a flow of carbon around the landscape. So we also have carbon leaving the soil. So through plant and soil microbial respiration, so just like us, they respire. So you have naturally this loss of carbon dioxide leaving the soil. If we're tilling the soil, we make that more rapid, and so we have more carbon dioxide leaving the soil. So that's perhaps a less efficient strategy, but a necessary strategy in some situations as well. Carbon dioxide from fire, so if there's been a natural fire or if we're burning paddocks, for example, there's a loss of carbon dioxide with that as well. The one where I have a complete no-go is the carbon loss through soil erosion. So where we've got fine sediment which leaves our paddocks and moves somewhere else, often it makes that soil carbon more exposed to decomposition. That's also a loss of carbon. That's like a really missed opportunity. So the more soil we keep on our farms, the better. And the practices which are growing soil, the better as well. So that flow of carbon around the landscape is happening in this paddock here. This is like down south. This is one of our farms, a Flera subclover paddock. 2 farm managers hiding there while I'm just waiting for Susan to finish her monitoring, not helping. This multi-species cover crop, so the flow of carbon is still happening in this environment. It's happening in this environment on one of our farms out west at Condo. It's happening out the door. It's happening in Queensland. So the flow of carbon is happening. What you can influence as land managers is how big those arrows are, right? So how much carbon is going into the soil? Are we optimising the length of time that that carbon stays in our soil, which will be minutes to days for carbohydrates. It's going to be longer, days to months for particulate organic matter, but if it's nice perennial pastures stored deep in the profile, it's going to be decades to hundreds of years, and then we've got that really stable pool of microbial carbon as well. So increasing the flow of carbon into the soil via plant growth, making sure that we've got perennial pastures where we can, or practices which are keeping cover on the landscape as well, so that we reduce the loss of carbon. So that's the carbon flow and thinking about what we can and cannot influence. So if I was me, and I frequently am, I'd be like, it's quite simple, right? Like, so I'm going to bury you in the literature just so you've got the table, so you know I'm not making shit up. But we've got the data. So when we think about our ACCU scheme, it needed to be evidence-based, realistic expectations. So the data is there, and that's why we've got one of the best soil carbon methods in the world, right? And that's why, because we've got evidence that support it. Now, that is not the same to say every practice works everywhere all the time. Decisions need to be context-based. So what we have here, and you'll get access to these slides, it's a list of regions in the left-hand side, global meta-analysis, where we look at lots of different papers, through to more local studies in New South Wales, management practices, lots of letters there. The main things to remember are pastures, soil nutrition, legumes, and grazing management to maintain ground cover. That's where the evidence is. In Australia, we look at carbon, or internationally, we report soil carbon to 30 centimetres, but with our ACCU method, we can count carbon deeper as well, but we've got less data on subsoil carbon. And just a point here, just because we don't have, like, an absence of data isn't evidence that something doesn't work, right? Like, so just be very, very careful in your critical thinking around that as well. But all of this to say that we have evidence around practice changes, and we've got around the sequestration rate that can be achieved with this. So it can be minimal if you're already up the top end of your carbon sequestration curve. If you're starting from a lower baseline, then it might be, do not look at this red box, look at the one on the screen, it might be more. So what this says, and actually, do you know what, don't look at it, look at me, because you're going to get this later anyway. What it says is, if we're thinking about increasing soil carbon, the first thing is, how big is the bucket? The bucket on your farm is decided by the amount of clay in your soil, first of all. So the more clay, the bigger bucket you have to increase soil carbon. The next part of the bucket analogy, though, is how full is the bucket already? If you've got a big bucket and it's already full because you've been maintaining your pasture nutrition, good ground cover, perennial pastures, good legume content, then perhaps your bucket's already full, so the increases might be minimal. still can increase soil carbon, but it might be a little bit harder to detect. That's why it's really important to think about sampling strategy. Sandier soils often have a lower carbon concentration anyway. So soil type matters, and that determines the bucket size. Initial soil organic carbon concentration also matters. So what is your starting point? The other thing that matters here is that the soils will reach a point of equilibrium. So most of the increasing in carbon happens in the first 5 to 15 years, and then it starts to plateau out. And at that point where it starts to plateau out, it's that thinking now about what is the next intervention that I want to have to make that soil increase more carbon. So microbes become in partnership with the plants and their carbon supply, and they'll self-moderate. Any ecosystem does that. So that's the idea around the point of equilibrium. For the North Coast, we did some work a few years ago back when I was with DPI, and we looked at the potential carbon sequestration in North Coast soil. So we looked across NRM regions, and for the North Coast of New South Wales, the modelled increase in soil carbon that could be achieved if we could just increase 10% relative ground cover was 8 tonnes of soil carbon. That's not a big number, but the range was much bigger. So we can increase soil carbon in our North Coast systems. We've done the modelling to show that was, like, do you know what, when you work for government, you're like, get very, very good at being so conservative that when you step out in private industry, you almost lose the will to live when you think that you operated like that. So it is very conservative, and that should, if there's a number there and it's positive, we should feel good about it, because it's probably going to be a bigger number than that. I've always been interested in the outliers, and as a reductionist scientist, you get trained to like, boop, delete those ones because this is what everyone fits the curve. When we're thinking about innovation in soils as a living system, like that's just a really stupid idea sometimes. So scientific paper, absolutely do that. When we're thinking about innovation, explore the outlier and try and understand what's happening. So in this study here, North Coast sits about the middle of the guts of this table here. We actually showed with some of our modelling that if we don't do things differently with climate change, there may be a decline in soil carbon, right? So there may be a decline. We also showed that there are the practices and tools to increase soil carbon in this region, and if you could, it could be 3 to 4 times the amount of that 8 tonnes per hectare, that the uplift that could be achieved. So let's think about how soil carbon works for you. So you can do it, you should do it. It's really important for resilient systems. Let's think about what those production benefits are. So the first one, when we think about these positive correlations, so that basically means as one metric increases, so does the other. So in our soils, if we think about soil water and aeration, the more soil structure you have, so the more carbon you have in the soil, the more soil structure you can have, the more opportunity you have for water to infiltrate, be stored, but really importantly for you guys, you've also got that air exchange opportunity as well, so you don't have water logging. So what I want you to do is, I've spoken about texture, I've spoken about structure. I want you guys all to stand up. So I would like to welcome you to the soil. You are now the soil. And so every single one of you here is now a soil particle, right? So look around, we're not judging. Soil particles, soil texture is just particles of different shapes, really. Sands are really big, silt is the medium size, clay are the really kind of excitable small ones. So look around, no judgment, see everyone's different shapes and sizes, right? This is the soil texture, okay? The proportion of sand, silt and clay. Now what I want you to do, we're going to pretend that COVID wasn't a thing, that we're not, I'm from Canberra, I'm like sweating my thingo off. All right, get together in groups of 5 now. It's a good count, see if people can count. There is evidence now that soil can talk. Soil acoustics, freaking exciting. This soil can't talk though. So very quietly, get together in groups of 5. This is how I can tell who can count. It's usually the scientists or the government people that don't count well. Right. Nice. Okay. So what I have changed here is not the soil texture, same particles. I have changed the arrangement of the particles, which is our soil structure. Now it is soil structure which we can influence with our land management. So now if I'm a microbe zooming around the conference looking for a root, which is, I should not say that, but now, but for all of you who may be, I'm not here tonight, so now I have space to move around the soil. Plant roots can explore the soil for nutrients, for water. We know that by having well-structured soil, same particle composition, different structure, plant roots can explore more than 40 times the amount of soil for nutrients and water to get access to air. It's around those partnerships with microbes. So the way soil structure happens, as bacteria move through the soil, they create these little electrostatic charges which make the clay plates stick together. They come closer together. Fungal hyphae explores the soil and enmeshes soil particles. It exudes carbon to stick the particles together. As organisms break down organic matter, they exude polysaccharides. So substances will kind of enmesh and make microaggregates and then macroaggregates. When we've got earthworms and dung beetles and the macrofauna, they're creating big channels through the soil, which will help air and water and plants. Plants, when they have these partnerships with microorganisms, can share resources. So when they're stressed because they're in a waterlogged area, if they've got a partnership with a plant which is sitting slightly elevated, they can access phosphorus and zinc when they couldn't if they didn't have that partnership with the microbes. So it is really important to understand the role of management. So the way we build soil structure, cover, perennials, making sure we've got adequate plant nutrition, overcoming soil constraints. And in our sandier soils, this is even more important, but in our clay-rich soils, it's also important, and we'll see an example of that in just a minute. I'm going to get you all to keep standing, right? Do not sit down, because we're going to do something else in just a second. So if we think about the relative importance of this now, I want you all to take a big, deep breath, unless you've got some kind of... I'm just going to keep talking, so keep holding your breath. And if you have like a heart or a lung thing, don't participate in this, because I'm not liable for this, but someone else might be. Keep holding your breath. If I was to ask an agronomist what's the most limiting thing at the moment, that'd be nitrogen. Usually they always say nitrogen. You've got to put out more nitrogen. Nitrogen's too expensive. Heaps in the atmosphere. You don't always have to apply it. Anyway, heaps of nitrogen. If you ask a farmer where I'm from, it's usually water. Water's always limiting. For you guys, what is the most limiting thing sometimes? Air. Air is not something that you see on a soil test result, right? You need to use your eyes, a shovel, and your hands to assess that. So what we're going to talk about at the back end of this presentation is reconnecting with your powers of observation to actually make a start. I often get a phone call going, here's my soil test results, what do I need to do? If I haven't been on your farm, I don't bloody know. Like I could probably sell you something or send you to someone to sell you something. You need to actually be connected with what you're trying to influence. Okay, keep standing. One more thing. So nutrients are really important. 1% increase in soil organic matter gives you an increase in soil phosphorus, because remember, soil organic matter, 58% carbon, 42% other stuff, of over a tonne of nitrogen, over 200 kilos of phosphorus, 160 kilos of sulphur. Soil organic matter is a really important store of nutrients. Lastly, and very importantly, soil organic carbon is positively correlated. As one increases, so does the other with cation exchange capacity. So cation exchange capacity is the soil's ability to hold on to and exchange cations. So calcium, magnesium, potassium, sodium, aluminium. So go back to your seats, but don't sit down. Look around the room now, because we're still in the soil. Now, cation exchange capacity is determined by the amount of clay and the type of clay. So different clays have different charges. Clays are basically like a ream of A4 paper stacked one on top of the other, enormous surface area, but they're kind of nice and compact. On each of one of those pieces of paper, there's negative exchange plates. Costa's given me a high five. He's saying 5 minutes, hurry up. Negative exchange plate. So cations are positively changed. Clays have that ability to hold on to positive charged things because they're negatively charged. So we cannot easily influence the amount of clay in our soil or the mineralogy. But what also holds on to cations in our soil is our soil organic carbon. So now, if you look around, each of these chairs are our negative exchange plates, right, in our soil, and you are all cations: calcium, magnesium, potassium, sodium, aluminium. Now, if we get this half of the room to sit down, right? If we reduce soil organic carbon, so we decrease the levels and we remove all of those chairs here, these people would have nowhere to sit, right? They're now in the soil solution and they could potentially be lost. By increasing soil organic carbon, which is the one lever that we can do, we can increase the soil's capacity to hold on to and exchange nutrients. And now this half of the room can sit down. Perfect. All right, so we've got a huge amount of shovel-ready evidence to determine, it doesn't look like this when you get your hand out, hey? So anyway, to determine why you should adopt some practices and the types of things that it will influence in your farming system to drive key resilience metrics. So around being more disease suppressive. There's data now around the soil microbial response to make plants more heat tolerant, drought tolerant. So we're learning a huge amount in this space here. We've known for decades around the role of some of these practices on accessing nitrogen from the atmosphere, organisms which can help in partnership with plants to solubilise phosphorus. So we can see this, and in the science, last year there was a great paper that came out and it basically reviewed a huge amount of crops and pastures, meta-analysis, looked at lots of peer-reviewed literature, and it showed that by fertilising to 80% of the critical phosphorus level in these major crop types, there was only a 1.8% yield penalty. So you've saved at least 20% on your fertiliser bill, and you've increased soil carbon exudation through those plants by up to 30%. The paper went on to say by halving phosphorus application, it was still only about a 2.1% yield penalty. So you've halved your fertiliser bill, still growing pretty much the same amount of product. When we do these trials, we hold everything still, right? The environment does not. You know, it might not rain, it might dry. There's a huge amount of planning that goes into to some of these agronomic decisions. What we're seeing in the literature now is that plants are doing what they're biologically and evolutionarily designed to do, which is make a partnership so that when things aren't going perfectly, you can scavenge for nutrients. That's not the same as saying you don't need to apply nutrients. It's the same as saying that we can actually lean into some of these situations a little bit more. I'm not even going to go through this because it looks weird on the screen, but the 5 things that we're going to talk about now to finish is around these 5. So Jess said, give people 5 things to go away and do rather than just get everyone to hug in little soil aggregates. So this is it. First of all, start with your context. So on our farms that we manage, the first principle is context-based decisions. So understanding soil types, rainfall patterns, climate, what you're growing where, mapping some of these is really important, and it's quite easy to do now. So map and prioritise your land, because if you don't know which soil you're standing on, every other soil decision you're making is guesswork, right? So dig a hole and have a look. Speaking of dig a hole and have a look, second step is around practices which grow more soil. So this is a concept where we look at growing the aggregation and soil down. It is really hard and expensive to buy more farms. It's better to make your farm more productive. So growing and stacking the opportunities in your farm is really important. So what's the thing to do? Go for a walk, dig a hole and have a look. So I asked Abby to bring in a couple of soil samples here. Abby, do you want to hold them up? And so what we say, go for a walk, dig a hole, ask yourself 3 simple questions. So 2 different different plant covers here. First of all, the thing that you would ask, and if you want to hold up the one with plant roots, is that, are there living roots in the soil right now? Okay? In this one sample here, we've got living roots. Okay? In this soil sample, which you can't hold up, there's no living roots in that soil. So are the pastures regrowing? How are we on top of it's rest and recovery phase in pastures, right? So grazing is not just about rest, it's about rest and recovery. Are the plants recovering? Is the soil protected? The next thing I want you to have a look at is, this is hard up here. I still kept it as the bare soil walk, but you could think about this when you're walking around on a 50-metre transect, either looking, depending on your system, for bare soil, or looking whether or not you've got an actively growing plant. And it's nice and simple. Think about a handspan. How many handspans of either not actively growing or bare spots do you actually have? And then what's the decision you're going to make when you see them? Like, what could you do differently? Is it around traffic? Is it around grazing management? Is it around needing to re-sow? So thinking about it and just make a decision. First of all, do the walk. Second of all, just have a think about what you could do differently. And it can be as simple as that, getting started. The third thing is feeding soil biology, don't fight it. So thinking about how we use fertilisers and the sides in our farming system, they are really important tools, right? They absolutely are. But just being really conscious in the decision about how we use them and when we use them. So maybe just for one, if you want to do something, go back and look at your last fertiliser or chemical application and ask 3 questions. First of all, did I apply it because of a measured need? Or did I apply it because I've always done it? It's always do it this time of year. You just got to do it just in case, okay? And just have a think about it. The next question is, was the timing chosen, and you can't do this all the time, but in some situations, was the timing chosen to avoid stress on soil biology? Are you avoiding waterlogged soils as a good example? And then the third thing, just to think about, like, this stuff costs you nothing, right? Just a bit of time and your eyes and your brain. Could it be delayed, reduced, or more precisely used? Could I do something differently? And the very last one here is measure what matters. So in the slides, I've got some key metrics to measure, but set some permanent monitoring points and just make a start. And if thinking about that is too hard across a big farm, just set one or a pair and just make a start. And it doesn't have to be expensive. It could just be looking at these 2 different spots in the landscape. And I want you to think about, what would you do differently? Just having that thought. So these are the types of things that we do with our farm managers at Impact Ag, just reconnecting powers of observation and patterns of decision making, and just being present and asking, do I actually need to do it? Could I delay it? Could I do it better? What's the next step? But don't delay in that part there. So if we just, that's the last there, the key messages, just there. You are the most important thing for land management and building soil health on your farm. Then the plants in partnership with the microbes.